All right, thank you. Thanks a lot, the organizers, for this wonderful week and giving me the opportunity to speak and to be the last. So it's a challenge, trying to entertain you. I think you should go to see Pharrell Williams tonight. It's going to be more entertaining, but for the time being, I changed the title of my talk compared to the written schedule, just because I initially thought about talking about cancer mutations and this kind of thing, but there has been so many amazing talks that I thought my talk was kind of not as good, and being the last one, I wanted to do something different. So I just tried to talk a bit about more general things about machine learning. We heard, I think, was it Ben or someone saying yesterday that for some, computational cancer biology is machine learning because we do so much of data-driven approaches. We start from data, we try to learn models, and we hope they will work. There was not so much machine learning this week, so I thought that this one talk related to that would be nice. And in particular, trying to express, so I work in this field and trying to express my feeling that there are many open questions and very much unsolved problems that probably some people need to address in the learning part, independently of how smart we are in designing features and diffusion and recovering subtypes. All right, so let me just motivate the talk, but I will not go to technical applications about specific cancers, etc., but just try to give some broad pictures of the problems we may want to solve. So typically, one application of what we do is improving cancer treatments, and this can be achieved by having better diagnosis, having better prognosis, meaning predicting the risk of relapse, etc. Hopefully, at some point, being able to predict if a drug will work on a patient, so predict drug response. So all these things are usually important problems. And ideally, this is a very old picture, but ideally one approach would say, well, we have a patient, we measure whatever we can measure, we sequence, and from this we put in a computer, and the smart computer will tell us, well, for this patient, don't do anything or give that drug or follow this treatment. That would be a dream that perhaps will be achieved in 20 years. But for that, we need to solve the problem of how we go from the data we measure to the decision or the prediction. So one approach to do that is data-driven, and it's, so here I just focus on a binary phenotype, let's say response or not to a drug. Machine learning is the discipline that is one discipline that tries to address this. Saying if you collect data about samples, and let's say samples respond or not to a drug, then you can plot the samples in a space. Suppose here I have 19 patients on which I measure 2 genes. I can plot each patient in a 2-dimensional space. I color the ones that respond or not, and then you instantly see that it's easy to see there is a difference between the responders and the non-responders, so you can learn a rule, and then when you have new patients, we'll make a prediction. Right? This is a cartoon example of what machine learning could be about. And the way to solve, to find this design, there are many ways, there are many algorithms that you know, that you've heard of. You can make neural networks, random forests, supervector machines, lasso, whatever. Some methods, for example, I just write a few equations, but to learn a line, you optimize over the set of linear functions, over the set of lines, the functions that best separate the black from the whites. Okay, you define some objective function, you minimize it, you get a classifier. This will be your predictor at the end. Okay, so this problem is pretty much solved. Okay, there is not. It has been solved for decades. There is no question about that. Now, what's not completely solved is when you reverse a bit the numbers and you don't have 19 patients in 2 dimensions, but you have like 2 patients in 19 dimensions. Or to be more realistic, you sample, you sequence patients, and you end up with, let's say, if you're lucky, thousands, tens of thousands, perhaps hundreds of thousands of patients on which you measure millions, perhaps billions of markers. Okay, so the ratio, number of samples over dimension or number of markers is inverse compared to the 2 to 19 ratio. Okay, and this thing becomes a difficult problem from purely statistical reasons. Okay, in terms of learning, it's just hard to learn when you have just a few samples and many dimensions. So there is a lot of work. Many people are interested in this problem because it's not only in biology, but in many fields. We have many features, a small number of samples, and there are many smart techniques that try to address this problem. However, it's fair to say that there is no magic tool that solves this problem. And probably depending on the data we have, depending on the applications, some methods will work, some methods will not work, and it's still not completely clear what works and what doesn't work, like feature selection or these kind of things. There is no general recipe. Okay. So something the thing I will discuss now is one approach, one which is quite trendy, I would say, if you've heard of deep learning, all these things. It's an approach that says, well, when you have data, so deep learning is more about images or text, but here, assuming we have this data, there's a question of how can we change the representation of our data, and instead of directly working with the raw data, so instead of saying we have a patient which is a set of numbers, what I measure, and I make a linear function on that to make my prediction. What about changing the representation, meaning going from the raw data to some other representation, which could be a vector, which could be something else. So you change your data to something else, and then you learn something on this new representation. Okay? So this is something quite intuitive. It's something like, it could be like, one approach would be to say, well, what about reducing the dimension? If I complain about the dimension being too high, I could try to say, to do gene selection, saying that instead of all the thousands of measures, I just focus on 10 of them. I'd have to choose it. And then the situation is easier. So feature selection is one way to change representation. There are other ways that we've heard a lot about this week, like if you have, the mutation spectrum of patients, instead of working directly with that, first do a smoothing on a graph, you get a new representation, and you hope that this representation will be better to make a model. Okay, this kind of thing. So more generally, you could ask, well, how to change representation? And when you think of that, it means what would be a good representation? It would be a representation that keeps the signal or improves the signal, the biological signal that would allow you to make a prediction. That's one thing. And the second thing, you want the new presentation to be amenable to machine learning algorithms. Like you want a representation where learning is easy. Okay, and so this part of how you go from the raw data to data where you can learn a good model, I think is a very open field, which is very active nowadays, not only in biology but in other application domains. So I will, to make this a bit more concrete, I will just now discuss two things which are by no means representative of the generality of this approach, but at least try to give some insights of how we can think of new representations of the data that sometimes may allow to improve the learning and therefore the performance of the model. Okay, if at the end of the day we want to make a good prediction, then this is what our focus may be, as opposed to trying to understand the full biology. Here I'm just talking of how can we make a model that predicts well what we want to predict. So I will talk very quickly of two things. One joint work with Marin, who gave a talk yesterday on how can you make supervised normalization of your data. And the second will be about how can you learn from, change your data by doing pairwise comparison between your markers. So let's start with quantile normalization. So usually it's a topic that's not very interesting. When you do machine learning, you first want to have good data. You hope that someone before you has processed the data, has made the bad work of going from the raw data to data you can use, and then you learn your model, or you do your diffusion, or you train your things. Now, what is full quantile normalization? This is something that is done, I think, in not always, but in many data that we use. It's simply the idea that suppose, so this is a top picture again, where suppose each box plot on the top picture is a set of markers, a set of numbers you measure on different samples. So samples could be patients. So you have each box plot is a patient. You do RNA-seq or you do transcriptomics. You measure the expression of all the genes. And usually when you compare the patients, you see you have huge batch effects. You see you have many things that at the end of the day make the distributions of the values very different. Okay, so you could just stay like that, and if you stay like that, you do clustering, and you see very clearly the batches, the non-biological effects, so you would like to remove that. One way to remove that is not always done, but one common way to do that is say, well, first, for each patient, let's try to normalize the data so that they have the same coverage or the same average, or make something comparable. And for example, full quantile normalization is a very strong approach that says, let's impose that each patient, after normalization, has the same distribution of values. Okay? So it's easy to do. The way to do is for each patient, you have, let's say, your 10,000 measures. You rank them for all of the patients, and then you choose a target distribution. That will be the distribution after the normalization. And once you have your target distribution, you just modify the values you had before normalization so that they have the same ranking, the same order of the features, but they fit the distribution you want. Okay, And so often this is done. There is a question which is what should be then your target distribution, because everybody is normalized to the same one. So it could be, usually it's the average distribution of all the guys, but it seems a bit arbitrary. It could be whatever. But at least you end up with things that you hop. So when you do that, you see you have changed representation of your data. And the hop here is that you have removed bad signal, like technical artifacts, and you hope that you have kept logical signal. So it's a bit in this idea to say, let's change the representation in order to learn from data which are better. It turns out that this thing could be important, and here I will just, I will not repeat all, but this is a slide that Marin showed yesterday. So in fact, this work was motivated by this application, where, to make a long story short, here the goal was to train a model to predict survival of cancer patients from mutations. Okay, so you have mutations, you want to make a model to predict survival. I skip all the technical details, but the take home here was that if you work on the raw data, so you have a vector of binary vector of mutations, it's very hard to run a model because there is not enough overlap between the patients. So you get bad performance on the raw data. Now, nice idea, you do a diffusion over a protein-protein interaction network. Then suddenly it's nice because it's motivated because you have mutations in genes which work together. So as soon as you diffuse, you start to get overlap, and you can hope that it improves. It improves a bit. It's called NS here. So here it doesn't improve at all. Here it improves a bit. But you see, it's not, something is still missing. And now, the devil is in the detail. This is what I call the machine learning part, which plays a role. If then, instead of just doing network smoothing, you do full quantile normalization, which is done in the packages which are used. Sometimes they are not very much highlighted in the publications, but they are done because otherwise it doesn't work. Then you get a boost in performance. Okay, so just to say that the simple, like let's say the idea of smoothing is great, but to make it work, you need to combine it with some purely mathematical artifact so that the learning can occur. Okay, and in fact, if you change if you still do full quantile normalization with a different target distribution, you can still improve or at least get different results. So here I just want to say that whatever these results, this is the part of thing that's often hidden from the. It's hard to understand why it works or why it doesn't work. But it's my experience is that when you run these big black box models, high dimensional models, sometimes the reasons why they work or not is a bit hard to get, and sometimes it's not only what features you get. I mean, you may have very nice ideas of we need to get these features about interactions, about this, but at least to get a good performance, there are a few things which are still very fuzzy. In this case, the way you normalize the data plays a major role in the performance of the model. All right, so you could say, well, here, I took mutation data, I diffuse, I quantile normalize, it works. But as I said, there are different ways to do quantile normalization. You can choose, for example, the target distribution. So you may say, well, if I quantile normalize to get a Gaussian distribution, would it work better? Or if I keep the average distribution of the data, is it better? Or if I just threshold, like a very, what Marie did, a very different normalization, does it work? So it raises a question, which is, could we optimize the way we normalize the data and perhaps not do that independently from what we do afterwards? Not going from raw data to normalized and then do something, but joint everything. So this is something that we try. So the question now is, what would be a good criterion, a good idea on how to optimize the target distribution? And one idea, and I'm sorry for the equations, I know it's a bit late in the week, but here it's just, the idea would be say, well, if you think of going from raw data, doing full quantile normalization, and then learning a model, let's say a linear model in this case, which includes support vector machines or survival logistic regression or lasso or whatever. So here you learn a model. The idea is that what you want to do is to learn a linear model. So here the parameters in my equations are W and B. So this is a linear model, Wx plus B. This would be a linear function. And instead of learning it on the raw data, you want to learn it on the data which have been transformed by full quantile normalization. And here I just write a small f to indicate that f would be the target distribution. So usually what we do is we fix a f and we solve that to normalize and then learn a model. One idea to automatically choose what would be the best distribution, we'd say, well, what about including f here, so the target distribution, as part of the objective function, and saying, let's jointly optimize the way we normalize, followed by the way we made a linear model, so that at the end, we optimally predict survival, for example. Okay, so it's just the idea to link together the normalization and the linear model.
But
so
isn't it just connecting two functions, because it's in a way a linear function of f, so in a way.
Exactly. So I come to that. So
is it really new I mean, is it really different from saying I'm optimizing 1 over 1 function that is?
No. So I come to the next slide. You would see it's very at the end of the day, it's not very new. It's just okay. Let me continue next slide. So here I just added f. I just say let's optimize our W and f, and we say, well, so let's write it a bit differently to see if this is not something already done or none. In fact, it's not very complicated to see that doing a quantile normalization is just, in fact, doing a matrix product, meaning that if you have a sample X, I said that matrix multiplication is two things. First, you rank the features of the sample, and then you give them the values of f. Okay, so this you can write as if I have a sample, I rank them, I put them in what's called a permutation matrix. So this is a square matrix which is binary with just 1 per row and per column, and the one says that the ith feature is ranked at the jth position. Okay, so if you replace your sample X by this matrix by X, then the operation of quantile normalization is just multiplication on the right by the target distribution. This gives you the normalized feature. And then the linear model is just multiplication of this on the left by a vector W. So you can combine all together and reinterpret this thing as just saying that what you have extracted from the original data is just the permutation matrix. So each sample from the raw data is transformed into a ranking of its feature. And doing a linear model over an optimized full quantile normalized data is just making a linear model over this matrix, just because you can play with the matrices. Okay? So as Nico was saying, this is something which is not completely new. You can recall that a linear model over a new representation of your data, which is a permutation matrix, with a few constraints, which is that this linear model, so it's in the space of matrices, so it turns out that it's a rank 1 matrix, so it's a constrained linear model. In addition, which could have specificities, like usually the target distribution has to be increasing to be a distribution. So it's a kind of variant of linear models where it's a linear model over matrices with rank 1 model that has the property that the f value is increasing. Okay, so I'm not sure it's very standard, but at least it's just a different way to learn a model. All right. So this thing is not easy to optimize just because it's not conveyed because of the rank 1 constraint. So at the end of the day, what we do is just a greedy approach where we optimize FW until it converges to a local minimum, and it gives, in principle, a F and a W that is jointly a normalized target distribution and a linear model to try to predict survival if we focus on survival. All right, so this is very much work in progress. So I don't have any. Well, the first thing I can say is that it doesn't work very well. I mean, we tried it with HOP, and sometimes it works magically, sometimes it does not. So after spending a few hours, we can get some curves that start showing that on some data sets, if you're careful, you can improve the performance. Here, what this shows is each curve shows the performance of the model after a number of iterations. So black is you train on the raw data, and then there is a curve 2, which is once you do 1 iteration of optimizing W and F, and you re-optimize, etc., it will converge to something. This is concordance index on some breast cancer thing. There is no strong message here, just that after struggling a bit with something, we managed to get something that does a bit better than the raw data. But it's fair to say, I mean, perhaps Marine has new results, but it's not magic. It doesn't work very well. But at least it's an idea to, that could be worth investigating as a tool to try to change representation and say, well, what about including normalization in the learning process? Okay, so let me move on it was done before, but it could be seen as a follow-up of this. In fact, what we have done here, so you understand that this optimization of the quantile function and linear model is equivalent to working with a representation of your data where on a sample, once you have the measures, what you keep is just the order of the features. Okay, it was the permutation matrix, so it's as if you were saying, I measure many things on a patient, I rank them, and I do something out of this rank. So this could be this idea to rank features and work on the ranking could be beneficial for machine learning, just because you remove the continuous aspect of the features, and you move your sample to a discrete space, the space of all possible orderings. It's a group, the permutation group. So it's a discrete object, and in some situations the learning problem may be easier in this discrete space than in the continuous original space of vectors. So let me quickly discuss whether there are other things that you can do if you decide to first extract from your data just the ordering of the markers, of the features, and then do machine learning on that. What else can you do instead of supervised quantile normalization? So in fact, the idea to look at ranks is not new, and I would just mention a line of work by Don Gieman and some follow-up on predictors. So this is all 10 years old work, but I think still relevant in many applications, where as opposed to making big linear model with 70 genes, etc., or more, or black box SVMs, for classification of microarrays, there has been a few interesting results where, in order, suppose you measure gene expression of samples, and you want, in this case, to discriminate between, this is very old and classical example, discriminate between two types of leukemias based on gene expression. It has been found that sometimes with very simple classifiers based on pairwise comparisons, you get good results. So pairwise comparisons means that to discriminate between these two categories, which would be the black and the white points, instead of making a linear model on the genes, you just have a rule, something like, is gene A larger than gene B, or the other way. Okay, it's a pair. So the benefit of that, one benefit is that this kind of rule is independent on systematic batch effects that would increase or decrease all values, like the pairwise comparisons could be robust to some technical effects, and sometimes it may lead to biology too. So this is, I don't want to do that, but because you have genes, you could say, well, if my rule is based on comparing 3 genes, at least I have a rule that perhaps could lead to some explanation. But let's say that at least the idea not to look at the value, not to make a predictor based on the value of the gene expression, but just comparing the values of different genes has been around for a while. So what we can try to do now is to go a bit further and say, well, what about working in this representation? So again, for me, it's a way to say, I measure data, but I don't want to work directly here, too high dimensional, too complicated, too much noise. Let's try to replace this thing by something else. And in this case, the something else could be just a binary matrix. So here, this is one sample, so think that each row here is a gene. Okay, and replace a measure on all the genes by a matrix where you just compare all genes 2 by 2. So you take gene 1 versus 2. You check which one is the largest. So if the value here is larger or not for 1 or 2, and you put 1 or 0 in the corresponding row and column. Okay, so because if you have p genes, then you have p times p minus 1 divided by 2 pairwise comparisons, and you end up with the representation of this vector as a matrix of binary matrix of size p times p. Okay, and you say, well, what about working in this representation? Like if I want to make a linear model, instead of making a linear model here, what about making a linear model here, just using these features of pairwise comparison? This could be one approach. So again, I don't claim it will work, but at least it's a change of viewpoint, and perhaps you could argue that there are, dimension is bigger here, but it's just binary. So, there could be some trade-off that says it may be better to work with more binary features than with less continuous features. This could be tried at least. Okay, so let's try at least to follow up a bit these ideas. So if you want to do that, there is a practical problem, which is that if you measure, let's say, 10,000 or 100,000 or 1 million markers now, I say, well, you store your million-dimensional vector, and first you start by building this million by million binary matrix before doing your SVM or your logistic regression. So it's a bit a pain to do that. You don't want to really store these binary matrices because they are just extracted from the raw data. It seems to be a waste of memory, of time, of computation, etc. So here you see you have one matrix for each sample. So if you have n samples, you have n matrices of times p by p, and the p can be very large. This is our problem. P, the number of markers, could be very large. So how can you still work with this data? Well, there is, so this is the good old, for people in the room, who remember support vector machines and kernel tricks, etc. This is a case where, in fact, you can make linear models over these matrices using a trick, mathematical trick, which is that even though these matrices are big, it's very efficient to directly compute their inner product if you want. So if you see each matrix as a p times p minus 1 divided by two-dimensional vector, and suppose you take these two matrices, and you want to make the inner product, you think about it, the inner product between these two matrices would be the sum over all the boxes here of the products, so 1 times 1 or 1 times 0 or 0 times 1. So this would amount to count how many pairs of features are running the same way in the two samples. And if you look closely at it, in fact, this thing is a very standard measure of correlation between the two original data called the Kendall-Tau correlation. So it's something that everybody knows about. You go to R, you click correlation Kendall, you get this. And so here the trick is just that the Kendall-Tau is precisely the inner product between these two representations. Okay, so this is just a mathematical fact, but it's a good news for things like support vector machines or ridge regression or linear Cox models, etc. Because it means using some trick working the draw that you can solve the SVM without computing these matrices, but just working with the original data and changing the kernel. You say instead of making a linear or Gaussian kernel, I take the Kendall-Tau kernel. And this thing will allow you to very easily learn SVM, even though you work in huge dimension. Okay, so it's just a computational aspect of it that allows you to work in high dimension with fast computation. Okay, so this I think I can just skip. I still thought I would show a network because there are many networks this week. So technical comment, what I just said could be interpreted in different ways. If you think of all, I said let's represent a sample, so a patient by a ranking of the features, then you can make, so the set of rankings is huge. There are many possible permutations. It's called a symmetry group. In fact, you can imagine a space where you have all the samples, and you can connect them as soon as they have just a pair, so in this case, a pair of successive features which are reverse flipped. Okay, so this thing is called a Cayley's graph. And for people interested in this kind of thing, what I just said is that if you take in this graph the shortest path distance between two samples, then the shortest path distance is the number of inversions you need to make to move from one sample to the other. So this is exactly my Kendall correlation. 1 minus my Kendall correlation. Okay, so what we do in fact is that to compare two samples, we define a distance between two samples as the shortest path distance in this particular graph. And it's a bit of magic that computing the shortest path distance is so efficient, even though the graph is huge. And for example, there has been other attempts in machine learning to say, let's work on this graph and define a distance between things using the diffusion kernel, so the random walk ID that is very popular in this domain. It has been done, but the problem is that to compute the diffusion kernel here takes a super exponential time, because you cannot do better than really, in a sense, inverting the matrix, which is n to the n times n to the n. So this is a case where computationally it's much better to work with the shortest path distance on this graph than with any other variant of distances between nodes of the graph. But it's not central to the talk. It was just a comment to have at least a network, a graph on my slides. All right, I think I will just illustrate how it can work. So here, does it work? Well, we tested this. Again, it's not very hot data sets in these days, but at least there are benchmarks to say, well, what about how do we make models in high dimensions? We tested, we compared. Here we just say, well, let's just change the representation. So we try not to change the learning algorithms. We just took a support vector machine and say either we learn from the raw data, or we learn with a Gaussian kernel, or we learn with this or this, or we learn with this representation, meaning the Kendall kernel. And without trick or tuning too much, it turns out that this thing is competitive. It's not significantly better, but it's easily competitive with making a linear model on the raw data, or using the Gaussian kernel, or using the top scoring pairs, or a lot of variants. Okay, so again, it's not a huge win, but just to say that just this change of representation, it's hard to say beforehand if it will improve or not the performance, but here, at least, it's better to make a linear model over the binary matrix than over the raw data. Okay, for reasons that probably have to deal with the complexity of the learning in this space. So in the hope that we have kept enough biological information and try to remove a bit the noise, or perhaps decrease the dimension. All right, so I think I don't need to talk of some more early technical details. And yeah, I think everything else is just added thing. So my main message here was to say, well, machine learning is a nice idea, but be careful. It's not a solved problem in high dimension. And more importantly, my message would be, when we make a model, we reach a performance. It's not obvious how to improve the performance. In particular, what's the bottleneck? Sometimes the bottleneck is we need more data. Sometimes the bottleneck is we have too many data. Sometimes it's we don't have the good features. And I think this part of understanding why we have a limit is important, because it could help us to sometimes improve the limit. Sometimes, typically by doing things that seem not to make much sense from a biological point of view, like removing important features, but just because they could help the learning process by making the ratio number of samples over features less drastic. Okay, I think that's all I wanted to say, and I would just like to thank in particular, Marine is here, and Yunong. I don't see him. It should be Yunong is here, who worked on the kernel. And you for your attention until the last minute. Thank you.
Thank you, Teresa.
So I was wondering whether we can help with this intuition. So intuitively, it feels right to move to the relative information, relative ranking. But if we have a situation like with the, say, gene expression, where we have this blob of genes that are lowly expressed, wouldn't this introduce a lot of noise, because you'll have lots of comparison to? So would that be also require some sort of filtering? Would you expect this artifact of the signal being compared to, like, most of genes being expressed at the background level?
Yeah, so that's a very good point. Obviously, when you take all pairwise comparisons, 99% of it seems to be nonsense, probably. Sorry, the question was, here in my representation, I compare all pairs of genes, okay? And probably among all the genes, many of them have nothing to do, are very lowly expressed. So when you compare all pairs, you could assume, like, in my matrix, this matrix, perhaps if you take a gene that has a very low expression or noisy expression, it would just induce a lot of noise here. And perhaps the amount of noise would be more important here than in the original data. So that's a good point. I don't have any strong answer to that, except that we tried. So what we tried is typically, here I did not comment, but sorry, perhaps I have one slide. Yeah, this kind of thing. So what we said is, what about instead of taking all pairwise comparisons, to just pick the best ones? So top scoring is the one top pair. K top scoring is a method that says, let's take K top scorings. And so we tried, perhaps it's not perfect, but it's doing some feature selection of our pairs and say, instead of taking everybody, take the best pairs. And what we found in terms of performance, it's a bit not a very good graph, but we found that there was no benefit in selecting features in the space. Okay? So this may be due, to the power of the SVM to work in high dimension and be robust to noise, but it's a very good comment, and we just found that there was no benefit at all to do feature selection. Perhaps the feature selection itself is a difficult problem that introduces difficulty. Yes?
So could you go back to this graph that we compared the colors?
The performance, yeah. This one?
Yeah, I think, so first question is, do you have any reasoning for your Kernel color works than others? That was the first question. The second question is, looks like your linear color works better than high degree of polynomial color. High degree polynomial color works better than RDF color. That's sort of make prefers pandas, right? So usually,
Well, it's reverse.
works better than linear kernel, and arbitrary kernel works better than linear kernel.
My experience on expression data is not this one. On many problems, yes. I don't know if you have some particular result in mind, but so the comparison between Gaussian, polynomial, and linear kernel, it's surprising that at least in these data sets, if you systematically try, you will see that the linear kernel is very, very competitive. Probably it has to do with the huge dimensions compared to small samples, and we cannot afford learning nonlinear things. But let's say, there is not a huge difference, but at least on this data, I would not. My experience is that the Gaussian kernel is not really much better than the others. But regarding sorry, where I am. Yeah, I did not explain what all the variants were, but so this is just empirical finding. I don't have much explanation for that, but at least, if I want to explain what we try typically the linear. Just the standard linear kernel, either on the initial data or on the top was on the pairwise comparisons where the best were selected with feature selection in this case. Okay, so
How many features do you have?
well, the number of features is optimized by cross-validation. We say so what I call the linear top. This is a linear SVM after feature selection over the binary matrix. Okay, and the number of features itself, it's part of the learning process. So there is inner cross-validation to select K and etc. So it's a bit a complicated process. But this is where I say it does not really improve overtaking everybody.
But actually, linear kernel works better than the other kernel. That means your space is probably simple. That's why linear kernel works better. Your problem space are more complicated than actually the target or high degree of.
Yeah, you're right. But you could say simple, or you could say that in dimension 20,000, it's quite easy to separate 100 points. Of course, in our functions, you don't need much nonlinearities to separate 2 points in dimension 20. So it's related. If we had, I think it's related to really this idea of understanding what's the bottleneck. Is the bottleneck to move to nonlinear things, or the bottleneck to decrease the space? I think here this is more evidence that we are at the point where we don't need to go to more complicated models for sure, because we cannot learn them.
I have a question about batch effect. So, maybe you can extend some of the methods for cases where just ranking won't solve batch effect. There are many cases in the literature. So, do you have any ideas?
No, no, I don't have any particular idea. I think there's a huge literature on batch effects. So for sure, here we remove some part of problems which just keep the ordering. So systematic things or change of distribution. This is handled by doing full quantile normalization. Basically, that's why it was proposed. Now, I would just say, at some point, probably to make good normalization or to remove the things, we need to understand, to find directions, some kind of orthogonal directions. If we could find a representation where biology is this direction and batch effect is this direction, then we are done because we just focus on this direction. And I agree that the ranking is not so easy. It's very complex. So no, I don't have any magic idea.
Maybe I didn't get it. So you have two methods, and you started out by motivating we should decrease the dimension of P.
Yeah.
P is too big compared with N.
Yeah.
So does any one of these two methods actually decrease P? It doesn't, right?
Well, it doesn't. It decreases. It increases P, but it replaces continuous values by binary values.
In each P, in each of the feature space, and make it simpler.
Yeah. So typically, this is what we do. This is our initial space. So here it's a vector of numbers. Okay. So it's a p-dimensional vector, and I replace it by p square 0, 1 values.
And that's a simpler one.
Yeah. I mean, it's a possibility. Again, this is why I say that it's not a solved problem. Here you could say it's simpler because in machine learning statistics you can quantify that indeed the learning rates or the theorems that quantify how hard it is to learn with linear models are better here than here. Okay, you get a log factor when you move from continuous to discrete. But this is just theory. Okay. Here the intuition, I mean, there is not only the change of dimension, but again, perhaps try to find a representation that could be more robust to something that could pose difficulty to the raw data. So I think it's a mixture of all, but it's very much open. Myself, I don't have a clear understanding of what's happening, so this is very empirical.
So I had a question about the data sets you looked at, whether they were microarray data sets or sequencing data sets?
I think they are mostly microarray.
Okay. Because I was wondering, because with sequencing data, I mean, with microarray, it's reasonable to assume that you're measuring each thing reasonably same variability. But with sequencing, of course, you get different sequencing depths, and so your variability in how you're measuring them varies from gene to gene, not just across samples, but from gene to gene much more. And
yeah, so I fully agree. Yeah.
And it won't necessarily show up in across your sample as variability. It would be like within the ranking. So I was just wondering.
So we didn't think particularly about that, but it's clearly different types of data. And my idea would be say, well, for different types of data, let's try to understand what's behind it, and perhaps this idea of finding representations of features or systematic change of spaces adapted to the data are important. So for single cell, we have many zeros. Obviously, I don't want to rank everybody based on the zeros. We need to be smarter than that, for example.
Okay, I think we leave it here. Thanks
Thank
to
you.
both speakers.